Hello, your friendly neighborhood, Mr. Stone here, and we are going to be looking at today how to sort through permutations and combinations. Really, it comes down to identifying what you are looking for. The formulas themselves are not terribly complex, but you need to decide what is it that I need. First thing that we are going to look at here is the fundamental counting theorem. So say that you've got, let's say you're trying to put together an outfit. So you've got 3 shirts, 2 pairs of pants, and let's say you want to add in a hat. And you happen to have a nice collection of 5 hats. How many different outfits can you make given your 3 shirts, 2 pants, 5 hats? This is really going to unfold like a tree. You've got 3 options for shirts, so you can branch off originally into 3 different choices here. Then for each of those choices, you've got a split of 2, because you can go with different pants for each shirt choice. And then once you've made that choice, you can go on to 5 more choices from there. So what we're going to see is that if you take 3 times 2 times 5, that will give you your total number of options. In this case, we've got 30 outfits. Note that each one of these is unique. Your shirts are different from your pants, which are different from your hats. When you're looking at a situation like this, the fundamental counting rule of just multiplying these options by each other and having the tree, as we looked at a bit in class, will help you determine when to use this. Okay, so that is option 1. That is our fundamental counting rule. Now, when you're looking at the order of things, that's when a permutation really comes into effect, right? You need to think about, when am I going to need to put all of the items in order first? That's our most simple. So permutations, this is no replacement, nothing is repeated. And let's say I've got 9 people standing in a line, and I want to see how many different possibilities could I have to arrange these 9 people. Well, think about the number of spots that you've got. So I've got 9 people, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoop, 9. And in this first slot, I've got 9 people that I could put. And then, once I've put someone there, I've used them, so I don't have the 9 to pull from when I go to my second spot here. I only have 8. And then I've used another one, so that now I've got 7 to put that I can put in this third spot in the line. So similarly, it's going to continue on down the line, where I keep losing one person that I could put in for the next spot because they've been used. I put them into the previous spot. This is going to work similarly to how we saw with the fundamental counting rule. We just multiply all these times each other. And 9 times 8 times 7 times 6 all the way down to 1 is the same thing as 9 factorial. And in this case, if you plug that into your calculator, you will see that 9 factorial is this nice big number, 362,880. Okay. So this is just a basic permutation. You're putting all of the items in order, and we don't have any sort of replacement. Everything is different. But let's say that you don't want to necessarily order all of them. Let's say you only want to do a few. So let's say you've got 10 people that run a race, and you are only concerned with the top 3. Now there's 2 ways you can look at this. You can look at this in terms of kind of what we did just above, which is you've got 3 spots. How many people could go into that first spot? How many people could potentially win the race? Well, potentially all 10 could win the race. However, we've used 1, so now for our second spot, we're down to 9, and we're down to 8. Just like with the fundamental counting rule, we can multiply these times each other. 10 times 9 times 8 gives us 720. So we've got 720 possibilities that we could have for first, second, and third place. This is convenient here, but you may be dealing with some larger numbers. Let's look at the formula that would help us be able to evaluate this if we don't have something that's just so tidy here is finding the top 3. So the formula for this would actually be n factorial over n minus r factorial. And n is going to be our total number of objects or items that we're working with. And then r is our number, I'll say grouped. I like to say r kind of rank, but there's another reason we're going to use r for in a little bit. But this is the special number that we're pulling from. In this case, we said that we're looking for our top 3, so that's going to be our r. And the n kind of fills in for itself. N is usually pretty simple. N is also going to be, in most cases, your larger number. R can never be larger than n. N is always going to be greater than or equal to r. You cannot get your top 20 spots if you've only got 10 people running a race, right? So n has got to be greater than or equal to. So in this case, again, we've got our two numbers here. Our 10 would be n, and our 3 would be r. So I'd have 10 factorial over 10 minus 3 factorial. This is the same thing as, we're going to simplify what's in there, over 7 factorial. Okay, 10 minus 3, 7. Here's where it gets interesting though. 10 factorial is the same thing as 10 times 9 times 8 times 7 times 6, all the way down to times 1. Over, well, 7 factorial is 7 times 6 times 5, all the way down to times 1. This right here on top is the same thing as this, so these are actually going to cancel each other out. Boom, boom. And we're left with 10 times 9 times 8, which is the exact same thing as we set up here. So you have two different ways of getting the same result. However, this one down here is the general formula. It's handy if you're dealing with numbers that are not as convenient as 3. If you've got to find like the top 20 positions out of 40 people, then it's not going to be so easy to multiply everything out there as we did right here at first. All right, so this is another option for permutations, and we're only concerned with grouping our top a certain number within there. So we've talked about permutations without replacement, but what if we've got permutations where items repeat? Well, let's say I want to find out how many different ways I can arrange the letters of the word success. Okay, so I've got my word success. We see we've got some repetition in here. I've got S's, I've got 3, and I've got C's 2. Putting these in a different order, like if I rearrange these two C's, that's not going to give me any different result. I'm still going to have the same word here, success. Okay, I can't really tell the difference if I'm swapping out these same letters. So we need to be able to figure out a way of doing a permutation where we account for that, where we say, okay, you know what, if my C's are swapped up with each other, that's going to give me the same result. So we're going to be looking for a little bit smaller number than if we just did, well, we've got 7 letters here, so I can't have 7 factorial, because that's going to be too big. That would, if I did it as this, that would be like I count each of these letters as being separate, like this was C1, C2. We don't care about that. We're going to see that they're the same. And what we can do for this is, again, our total number is going to be n. That's our total number of items. And I'm going to count my repeats. So this is repeating item number 1, so number of repeating item 1. In this case, my S's. So in this case, my N is going to be 7 because I've got total number of 7 letters, and I have 3 S's that repeat. Okay. I'm also going to have an N sub 2 here, and this is my number of my second repeating item. And this can go on for as many repeating items as you have. And I've got 2 C's, so that's 2. I don't have any repeating U's or E's, so really I can disregard them. My general formula for this is going to be n factorial over n1 factorial times n2 factorial all the way down to n however many. I'm just going to put k here, factorial, because this just stands for, I could have 1,000 things that are repeating. It gives me flexibility. We're not really going to see too many that get very big, but it is there if you need it. But let's see how this works so that you can, and you'll get a better grasp of how to use this yourself. So we're looking at success. So I've got 7 letters in success. So we already said my n is 7, so I'm just going to plug that in right there. I've got 3 of my first repeating letters, so I'm going to put 3 factorial down here. And then 2 factorial for my second repeating letter, because we said that for n2. And I don't have anything else that repeats, so really all the rest of this here I don't have to worry about. I've already got all my repeating letters. That is done. So right now I'm left with 7 factorial, my n, over n1, which is 3 factorial, times 2 factorial. Simplify this out, and that just gives me 7 factorial over these bottom ones. Are so nice. You have to multiply these out together. Well, 3 factorial is the same thing as 6, and 2 factorial is the same thing as 2. So basically you've got 7 factorial over 12, which will give us 420. And that's it. If I, again, we said if I just did 7 factorial, this actually would be 720, which is a much larger number, but we're accounting for the fact that if you swap some of these out, you're going to have the same thing. If you move the 2 C's where they are in the combinations, or if you move the S's around, you're going to have the same thing. That's why we've got this stuff on the bottom down here, to make the number smaller, to reduce it, because it's otherwise you've got a lot of combinations that are, or excuse me, permutations that are essentially the same thing. All right, and now let's look at one more thing here. So permutations have order, but for combinations, we are not concerned with order. Order, not important. So let's say that you've got 12 candies, okay? They are all different. Maybe think back to your wonderful days trick or